Hi there. This is Maggie from Kaggle, and we are here with the third place winners call for the WiDS 2021 Datathon. So I'll hand it over to Sharda so she can introduce herself from the WiDS team.
Hi, everyone. My name is Sharda Kadanidi. I'm Kaggl's co-chair of the WiDS Datathon this year, and it is my pleasure to invite this team. And I'm really looking forward to hearing their presentation. Thank you so much. Congratulations.
Thank you very much, Sharda. Okay, so I can start. So I'm Saghiv, and I'm coming from the field of industrial engineering, operations research, and optimization. I'm an industrial engineer, and I also have an MBA. So much of my experience is operations research, but in the business world. And I'm also a PMP, which is a project management professional. So I also bring the skills of project management into this world. And I am also a certified data scientist by the Technion, which is Israel's Institute of Technology. So I combine all of these skills and expertise together. And I have my professional experiences in many industries, defense, high-tech, transportation, government. I worked in all kinds, in analytics for many years and project management. And actually my next goal is my first role as a data scientist, as this field emerged during these recent years, and I found myself very, very interested in that and also specializing in that. So this is my next goal.
I'm Liz Cohen. My BSS is medical engineering, and now I'm a student in the master in electrical engineering. I'm a deep learning researcher in NSC, and I do the ensemble part in this job, and that's it.
My name is Katz. I'm electrical engineering with a specialized in image processing and computer vision. I worked also for NEC as a researcher of computer vision, deep learning, and I am a Kaggle master, Kaggle competition master, and Kaggle notebook master.
Fantastic.
Hi, my name is Pavel. I'm also working for NSC. I'm data scientist for 5 years or like so. I hold a master degree in financial math from Bar-Ilan University. I worked for financial services and other, mostly financial services, telecom services, and others. That's it.
So we're Scientific Mind, the team from Israel, and we're very proud and honored to be here. We worked very hard on our solution, and we got lucky to get the third winning place. And we're very excited and positive about sharing our solution to make an impact. And we thank you very much for granting us this opportunity. So this is our agenda for today. We have slides with the background of each team member. We will present our summary, the feature selection and engineering, the training methods that we used, some important and interesting findings, and the final model that we used. And then we will leave, of course, time for questions. I will start with the summary, as we have a lot to share and a very short time to share it. And I will kindly ask you that if you have any question, to please write them down and ask them at the end, because I may answer them along the presentation. Okay, so these are the slides with our background, and now we will start the summary of our solution. So our solution was an ensemble of algorithms. The ensemble algorithm was logistic regression, and it ran over 120 models of the following algorithms: gradient boosting decision trees of 3 types, XGBoost, LightGBM, and CatBoost. We also use TabNet and also some classic methods such as logistic regression and random forest. We also used k-means for data imputation, which I will elaborate on later. So this was a very heavy ensemble and models, and it took about 24 hours to fully train the system on an average machine. And the hyperparameter optimization, the HPO, took even longer. Overall, it took a couple of days. So now the feature selection and engineering. So overall, we had 2,500 features to begin with. I will explain how we obtained all of them. And eventually we were, after feature selection, we were left with 1,000 features on which our ensemble ran on. The best, most informative features that we identified were many different insights from glucose, which is the direct medical logic, because we were examining diabetes. And we will present them in the next slide more specifically. We also found very informative the following features: the dialostic blood pressure, the hemoglobin, and the mean blood pressure, and also some kidney functions, the blood urine nitrogen concentration, the BUN, and the creatinine, both reflecting the kidney functions. There are also some very significant demographic features that we identified: the age, the weight, the BMI, and ethnicity, also in terms of genetics and environment, which both reflect they impact the probabilities of being diabetic, and also the GCS, the Glasgow Coma Scales of unable Apache, which is the severity of the illness. And this is our variable importance plot that we obtained using CatBoost, which was our best single algorithm in the ensemble out of the 120 models. And as we can see, the top 5 features are in direct medical and physiological logic of the dataset. Okay, they're all related to glucose. The most informative feature is D1 glucose max, which reflects the preliminary state that the patient was in, okay, when being admitted to the ICU. And then we have the remaining 4 features, which actually very interestingly reflect the dynamics of the patient during the first 24 hours in the ICU. Okay, the glucose mean, if the glucose level was decreased, indicators of the range. And I would please like to focus on this feature, the glucose range diff, which is a feature that we created. And we are very, very proud of it because it's very informative. And what it actually shows is the differences in range between the first hour, okay, glucose, H1 glucose max minus H1 glucose mean, the first hour range, and the first day range, D1 glucose max minus D1 glucose mean. And it's very informative because it shows exactly the dynamics, okay, which is hidden information in this data set, the dynamics of the diagnosis and the treatment and the patient's response during the 24 hours of the ICU. Which was very informative in terms of reflecting which patients are diabetic patients. So we are very proud of that, and we will also get back to it a couple of times during our presentation because of its high informativeness. So here we see the density plots of some of our important variables. This is the D1 glucose max, and as we can see, the higher the value is, the greater the probability is for diabetes. The partial plot of density plot of age. As we can see, most patients are between 50 years old and 80 years old, and above 80, we see less patients, probably due to mortality rates. This is the BUN Apache, the BUN, the blood urine nitrogen concentration component in the Apache diagnosis. And as we can see here as well, the greater the BUN Apache is, the greater the value is, the greater the probability is for diabetes. And here we can see our specific feature that we're so proud of and exactly how informative it is. And we can actually see that the greater that the range difference is, which means the greater the journey the patient went through, the medical journey, treatment, that the patient went through the first 24 hours in terms of diagnosis and treatment and response, positive response to the treatment, to the diabetes treatment, then we actually see the greater the difference is in range, the greater the probability is for the patient to be positive for diabetes. So some training methods that we used. So the metabolic state of a patient is a complex situation. And in order to understand complex situation, we need to use diverse algorithms and different models, and then to integrate them all together, all insights from all models. And this is exactly what we did here to understand the metabolic state and its dynamics. Okay, we believe in the NFL theorem. NFL standing for no free lunch, which means that there is no universally best algorithm for all problems. So our approach was to create a big amount of solid and as much possible diverse models to be able to fetch all the insights out of the datasets, all the insights that we could fetch, and then ensemble them into a single model. We first started out with a big number of models, 180 models. And then we ran logistic regression with L1 penalty, or a lasso regression. And the reason that we chose this specific regression is its ability to well recognize zero importance models in the ensemble. So actually we ran it a couple of times, and every time that we ran it, we obtained a more optimized score, a better score. And we identified some more zero importance models, which we could remove from our data set. And eventually that algorithm converged at an optimized score when we were left with 120 models, remaining all of them contributing information to the ensemble. Okay, now some important and interesting findings. So first we will start with our general approach, okay, to this great challenge and what we probably did more than other participants in this competition. So we recycled features from last year's notebooks and competition. We monitored all public notebooks for new ideas. We handled bias mitigation. Nothing works without it. And I will elaborate on this also later on because it's a very important challenge that we faced in this competition. We believed in our cross-validation, the CV, and our model, even if sometimes we got decreased scores on the public leaderboard. We still very much believed in what we did. And we took the competition very seriously and spent a lot of working hours on it. So now I will explain the first challenge that we decided to show here in the important and interesting findings. And it's the bias selection that we identified in the dataset, which means that the train set and the test set were different, and the algorithms trained on the training set, because of this difference, had difficulties generalizing to the test set and performing well on the test set. Okay, so this is exactly the situation where you use adversarial validation, the adversarial validation technique to identify this difference that impacts the quality of the solution, the quality of the model. So some features behaved differently in the train set and in the test set, and it made our model less robust, meaning predicting on unseen data was causing wrong results. So what we did was use the technique of adversarial validation, which is actually a technique where you use an adversarial model, which is a machine learning model. In our case, it was light GBM. We used this model and we ran it over a data set that contained samples from both the train set and the test set. So we ran this light GBM over this combined data set, and we tested its ability to classify, to identify which data was taken from the train set and which data was taken from the test set. And it actually performed very well and classified very well which data was from which set. And therefore, we understood that we saw this through the AUC score that was high of the adversarial model. So we knew we were in an adversarial situation that we had to handle. And this light GBM model also enabled us to identify the exact features which were causing this adversarial situation, these exact features which were different between the train set and the test set and were causing this situation. So we knew exactly which features to handle in order to solve this problem. And here is the map of the features. On the x-axis, we see the model the feature importance, okay, which means how much the feature contributes to the overall model, how much information it contributes. And on the y-axis, we see the adversarial importance, which means how much adversarial complications it adds. Okay, so features on the right, they have greater predictive power, they have more importance, and the upper features make the data sets more biased. They have greater adversarial importance. So as we can see, we have two outstanding features. We have the ICU-ID and the Apache 3J diagnosis. And if we think of the medical logic behind it, so they're actually correlated because the ICU-ID is the ID of the unit that the patient was admitted to. And the Apache 3J diagnosis is the code for the reason the patient was admitted. So they're actually related, and it makes sense in terms of the medical world. So these are two features that we obviously had to handle, and now we will focus on this area where the majority of the features is. And actually, we see another very interesting situation. We see many features that are actually on the y-axis, which means they have no importance, seemingly no importance, but they contain much adversarial information, much bias information, okay? They have high adversarial importance. And this is an arguable situation, whether to remove them from the model or not. Now, the model, so what are the arguments actually to keep or not keep them? The model importance was calculated, was obtained using one machine learning model, using the Katz model or best single model. So perhaps if we had used another model, these features would have the outcome would have been that these features do have importance, which is greater than 0. So perhaps they would have been important according to other models. And also another consideration is that the bias information is still information, even if the model does not have any importance according to Katz. So it still contains bias information. And if we remove that feature from the dataset, we lose this information. And it may lead to some important insights. So eventually we decided not to remove any of these features and to keep them all in the dataset. So how did we fix that this bias selection situation that we were in? So this is a little bit complicated, maybe a little bit complicated for people hearing this the first time, but I will do my best to explain it. What we did was actually encode the bias features in the following manner. For each bias feature, and there were about 6 bias features that we identified. So for each bias feature, we took all the data from both the test set, the train set, and the test set, because we wanted to disseminate the differences. So we had to take data from both the train set and the test set. And we took the data of all of these features, the mean, max, range, D1 glucose mean, D1 glucose max, all the mean, max, range, we had about 200 such features. And we took all their data from both the train test and the test set. And for each value in the biased features, for instance, ICU, okay, is a biased feature. So for the specific value of ICU equals 92, we calculated the corresponding mean, MEAN, the corresponding mean of, for instance, all of the D1 glucose mean values that were corresponding to ICU equals 92. So this way we created kind of a combined feature of the biased feature and of the mean feature, D1 glucose mean, for instance, which combined information from both the train set and the test set. So this way we could disseminate the differences between the sets. Eventually, we formed 1,200 features this way, because we had about 200 min, max, range, average Apache features and 6 bias features. So after creating all of those features, 1,200, we removed the bias features from the dataset. This bias was something very essential in the solution, not only in our solution, but also for other teams. Other winning teams also reported solutions that they used to mitigate this bias. And in practice, all teams who did not handle this bias, their performance was decreased in the private leaderboard position. So overall, we had about 2,500 features that we began with. 1,200 that we created during the bias mitigation, another 1,300 that were either given to us or created by the community or created by us, and later we saw that were also created by the community, such as H1 and D1 average and amplitude. The most informative features always appeared to be the ones representing the dynamics during the first 24 hours. Okay, and in our data set that was given in the competition, it was the H1 and D1 measurement. They were very important, and they actually point to the hidden information of treatments that were probably received. Medicine pill to stabilize the blood pressure, and other. And we think that if more such features would have been provided, features that that reflect either the dynamics of the glucose levels or other chemical levels, physiological measures that show the dynamic, or features that reflect the treatments that were received during these 24 hours, it would probably add a lot to the data and also impact the solution a lot, because we found them most informative. Okay, this is another challenge that we dealt with during our solution, and it's actually the data imputation and the data that was missing from the data set, or the non-available data that we had to complete. And we had to think how we complete it in the best way. And this is an example of a technique that we used, the cluster-based missing values imputation. And we used it in cases that the feature that was missing was actually dependent on other parameters. For instance, here we see in this plot, we see the D1 glucose mean values. Okay, and they are dependent on the BMI and the age groups. And as we can see in this plot, each group, each age and BMI group has its own healthy levels of glucose and its own mean of glucose, or D1 glucose mean in this case. And here we divided the plot into deciles. So we actually have 100 different values of D1 glucose mean, one which is appropriate for each cluster. And these 100 values, they vary from 99.31 to 126.96, or 100 different values between them. Okay, and those 100 different values, they're different from the total mean of all the D1 glucose mean values, which is 114.44. So if we want to impute this data in the most appropriate manner, we cannot simply plug in 114.44, because it may be healthy level for some age and BMI groups, but it will be an unhealthy level for many other groups, and simply plugging in this mean would completely disturb the data. This is why for this case, in this specific case of imputing the D1 glucose mean values, we use the cluster-based missing values imputation, because it was the most appropriate. Now we will finally present our model. So we have here two models that we would like to present, the ensemble model that we used and the best single model. And we will present their three scores, their CV scores on our computers, the public leaderboard score, and the private leaderboard score. So we ran this solution again after submitting it, and for some reason the score was dropped by 0.003 points, but we still remained in the third place. So this is the score that is shown here. And the best single model was a cast boost classifier that we ran on the data set, but before feature imputation, which was interesting. Now, another interesting point is when comparing these models, the differences between them is minor, okay? Between the best single model and the ensemble model, it's 0.004, which is almost insignificant in medical terms of diagnosis and treatment. But it is majorly significant in this competition because this is how we achieved the third place. So it really depends on what the goal is. If our goal was to select the best model for production, we would have probably selected the best single model because it is much easier to put into production. It is much less heavier. And in terms of medical meaningness, it's almost the same. So thank you very much for listening and letting us share our solution. And please, if you have any questions.
First of all, I really appreciate your taking the time. Thank you so much. I am really amazed by the effort that you all have put into the model. I'm really grateful and really, amazed by the effort, by the details that you've, the systematic thinking of the parameter of sort of feature engineering and what each of the parameters actually means. And I am really grateful that you put in that effort and that thinking. I'm so happy to meet all of you. Very talented, very committed, worked really hard on this competition and did fabulously. So thank you so much for taking the time, and thank you so much for sharing your results with us. And we're really looking forward to your submission. Hopefully, if you decide to submit, we're really looking forward to it. Thank you so much.